Welcome to part 2 of the Euchre Simulator project. In part 1 I introduced the game and the concept, and in part 3 I will review the results. Here I'll talk about the programming considerations. But if that doesn't interest you, I will have a few hilarious jokes. The simulator was built in R. R is an open source programming language used around the world for statistical applications. It can do more than that, but math and stats are what it does best. It was based on the Bell Labs S programming language, S and R being adjacent in the alphabet. Mathematicians are generally very clever. And I recommend the book The Idea Factory, Bell Labs and the Great Age of American Innovation. Anyhow, R is very powerful, but it's also a difficult language to learn. I do not have a computer science background, but have developed a powerful framework for making applications. I have not patented this system yet, so please cite me if you use this in your work, but here it is. Step 1, begin typing code. Step 2, an error happens. Step 3, declare the error impossible. Step 4, wonder when R broke and why no one said anything. Step 5, detect the error. Step 6, blame R for not giving a more intuitive error message. And step 7, return to step 1. So this process took ages. If there is a way to mess up this program, I have done it. Back on day 1, I got off to a great start and created a hubris that would haunt me for the duration of the project. Originally, I was planning to have the simulator play full games, as in you turn up a card, each player makes a decision, and if the card is turned down, the second bidding round commences. Then I realized that's unnecessarily complicated. Ultimately, I want to know whether or not I should play a given hand, so I cut straight to the chase and simulated what I want to see. So ironically, I built a lot of flexibility into the simulator that I didn't end up needing to use. I play each hand 1,000 times. So here I have a function that gives me a certain hand and then randomly deals cards to the other 3 players. You can see it gives a different hand every time I change the random seed. So if I loop this, I can deal 10 hands or 100 hands or whatever number I want, which ultimately ended up being 1,000. So in each case, player 1 stays the same, and the cards of the other 3 players change. This is intended to represent the universe of possibilities when you declare trump with a given hand. So here I have right, left, ace side 10. The resulting gains from these 1,000 hands will tell me whether this hand is a good decision or not. Really, this is the last part that went smoothly. I did this in about 10 minutes and was very confident. Making playing decisions is hard. I have 4 functions called the decide series. The code considers which cards the player has and then chooses one to play. There is some consideration of cards played thus far and limited contemplation of what the next player or players may have. If I had the chance to redo any part of the simulator, I would have made this more sophisticated. Even as it stands, these are the number of possible outcomes by player. So the first player has 8, the second player 13, third player 18, and fourth player 12. Just means there's that many unique paths along the tree before making a decision. Here's a tip. Actually map out this process in advance. I literally just sat down and started writing code like a moron. I'd run probably 500,000 games before realizing that one of the decisions in Decide's second player was incorrect. But I'm reminded of a line from That 70s Show. When challenged for not thinking something through, Kelso said, "Does an astronaut plan his missions?" That's how I live my life. Anyways, the code contemplates each of the decisions in a game and populates this table I called the game scorecard. It's called that because it's the scorecard for a game. I save one of those for every game played. So before I mentioned that I generally played 1,000 games per hand. Once that's done, the code saves a list of game scorecards to the computer's hard drive. I can then import the list and interpret the information. So I'll pick a list at random and look through a couple of game scorecards. So here I'll pick the 999th game from the list. You can see the completed game scorecard. Off to the right are the hands that each player had, and then it saves who played what and who won the trick. So in this game we won, and the next game they won, etc. That's really all there is to phase 1. Once the code was written, all I had to do was let the computer produce these games. This would have taken months until I was struck by the insight that I have more than one computer. So I transferred the code to 2 others and let them run night and day. I'm glad I did because I was initially shocked at how much faster my laptop ran the code than my desktop. I built the desktop myself, and before you make any smart-ass jokes, assembling computers is actually pretty easy, and the hardware itself should simply be better than that of the laptop. I'd read in an R programming book that the choice of hard drives does not impact speed of execution. That was clearly not correct. When I transferred everything to the desktop's solid-state drive, it ran about 10 times faster. I did go back and track down the author of that book, and the lawsuit is pending. So anyhow, for weeks I had all 3 computers running code. Here's the inventory of games played by computer. So a little more than 20 million games were simulated. Quick sidebar on number of simulations. I've done statistical simulations similar to this for my actual job, and one thing I hear a lot is, can you just run more simulations? You can always run more simulations, but past a certain point it really doesn't matter. Nerds like me delude themselves into thinking their little models can capture all of reality. And simulations are very appealing. You run it 1,000 times, you order the outputs, and then you can get percentiles. So you can say the 25th percentile of next year's US GDP growth will be plus 1.7%. The 75th percentile will be plus 3.9%. It's all pretty cool. And in the worst case scenario, you can do something similar. There's a number called the conditional tail expectation, also known as tail value at risk. You take the 5% worst outcomes and average those numbers. Nice and clean and very mathematical. The problem is that all this ordering and averaging obscures the fact that getting the assumptions right is really hard, and we usually don't. I realized this years ago, so I speak candidly about the risks of this type of modeling. Nothing brings it home quite like an example. We can find an instance where macroeconomic simulations swung and missed if we go way back to 2020. So anyway, later I'm going to look at whether 1,000 simulations was the right number. Again, if I didn't code the gameplay decision-making correctly, that won't matter. But I do want to know how stable the average is. We'll save that for the next video. So I ran a bazillion games and saved them to the hard drive. The next phase is the part I actually care about, and that is interpreting the results. Here the flexibility of R is very impressive. I can write a simple function that counts how many tricks my partner and I win. I am 100% certain there's a more efficient way to code this, but with my computer's power, I can afford to wait a couple seconds. You can see that I run the function on a given game scorecard, and it tells me how many tricks I won. R has the ability to apply that function across a list of game scorecards. So instead of writing a for loop, which can take a lot of time, I can summarize the output in a single line of code. So now I can see that of my 1,000 games, I got 2 tricks this many times and 5 tricks that many times, etc. Same thing with points. I think you can probably see where this is going. All I have to do is repeat this across all those lists, and I can create a giant cheat sheet that shows me the expected points from every hand with every lead. Up to this point, all of this code is specific to the base functionality, where a player decides trump in the second bidding round, or technically that plus when he picks up the turnip card and discards to result in the given hand. The other major subset of Euchre games is when a card is ordered. That fit relatively easily into the existing base framework. You'll see this function called discard. It's exactly what you'd expect. Given a hand and a card to pick up, which existing card should you get rid of? But even that was more complicated than I expected. The code for this simple game decision spans 746 lines. Of course, I'm not an efficient programmer, but still, a lot of this is trying to make sense of real game decisions that we typically make in less than 2 seconds. I asked several people what they would do with an unclear card configuration, and the responses didn't agree with each other. So once again, I'm introducing bias into the machine by making it play like me. Could do worse though, right? As I mentioned before, these numbers are only correct if I programmed the game decision-making perfectly. And spoiler alert for video 3, I did not. But on a relative basis, it's probably accurate to compare hands. So that's a look at the programming. The next video will go through the results and some interesting angles on the game of Euchre. Until then, thank you for watching.